Thank you. Yes, I wasn't sure. I had already sent out from the professional meeting conference, but it didn't. So I should be going.
Okay, cool. I'll try to make it good. So I want to run by.
Yeah, no, earlier is better than later.
Yes.
100%. Okay. Uh-huh. Yeah. Yeah. Have all people. Okay. Yeah, great. I think that's great. Person to do what? I am probably I am happy to make I'm happy to make a couple calls to help get people, but in terms of being lead role in organizing, we got an ERC proposal and ME Commons proposal, and got 4 proposals due in the next 4 months. So I can't take on any more right now. So but I'm happy to help in the sidelines or background. Okay.
All right. So maybe I'll talk to you.
John Mood? Well, he's on 2 of them. So he might go ahead and talk to him, but he might say the same thing.
Okay. All right. So I'll talk to other people too and see who can hire me.
Okay.
Yeah. Well, after
No worries. Much different than what I did before.
you in the lab.
No, Bill, well, we're going from MOCD all the way up through circuit time, so. But I think, total 5 year to get there. 2/3 of the way there.
What's the between system? You buying
We bought a used Nippon Sense. So. Now, yeah. It's always. In terms of undergraduate, or graduate. So I'm more sensitized to the graduate, right? So I think we, in terms of applicants, I think the number of applicants.
Okay, it's our honor and pleasure to have Professor Kish to our seminar speaker. So, Professor Kish is professor in electrical and computer engineering. He got all his BS, MS, and PhD degree from in electrical engineering from UIUC in 88, 89, and 92. And then subsequently he worked at HP Lab, where he co-invented and led the commercialization of all visible LED except blue, I guess. Right, this is the day prior to gallium nitride.
Well, it started out with red, orange, yellow, but eventually I was responsible for the blue at HP as well. But that was after the Nichia work.
That's right. Yeah. So and then after that he joined Infinera Corporation, where he co-invented and led the R&D and commercialization effort in a large-scale photonic integrated circuit and system on the chip for optical communication. So then he was a senior VP in the company before he joined NC State in 2018 or 19.
2018.
2018, yeah. So now he is he's the director of the NanoFab facility here. So he's a fellow of National Academy of Inventors, OSA, IEEE, and also a member of National Academy. He had 135 US patents and 170 peer-reviewed journal articles and conference publications as well. So let's welcome Professor Kish.
So it's a pleasure to be here today. And I'm going to talk today about innovations in materials that then lead to innovations in devices. And this is all under the context of hoping to, in addition to electrical engineering, a lot of the work that we do intersects strongly in material science. And so with this, hopefully this is some underpinnings to also become affiliated with the material science department as well. And so from that point of view, I will try to bring out where we really start in a lot of these innovations is with innovating in materials. And specifically what I have seen in my career is the formula for disruption is to innovate in materials, and it's that innovation in materials that allows you to then build devices that you could not build without that innovation or that capability in materials. And that's been kind of a repetitive theme throughout my career. And so specifically, I'll talk about some previous experiences today where work on innovating and developing aluminum bearing native oxides in 3,5 compounds led to state of the art in probably what's today the most ubiquitous vertical cavity surface emitting lasers. Again, advances in compound semiconductor wafer bonding that led to the highest efficiency red, orange, yellow LEDs, and then materials engineering advances in indium phosphide and silicon oxynitride that led to leading system on chip photonic ICs for communications. And then this all integrates together with what we're really trying to do here at NC State, which is really develop a wide bandgap and ultra wide bandgap photonic IC platform. And again, with taking and a lot of the trajectories in some of these earlier work. So I'm going to start out with work, and this goes all the way back to University of Illinois in the early 1990s to talk about work on aluminum bearing native oxide. And so specifically in the early 90s, and this was Professor Holniak, who is my thesis advisor, was studying this for years, was studying the degradation of high aluminum content aluminum gallium arsenide. And in an attempt to accelerate that study, put together a system where a nitrogen carrier gas was flowed nitrogen through a H2O bubbler and then into elevated temperatures, in this case 400 to 650 degrees C. And what came out of that, instead of being more degradation or faster degradation, was a beautiful uniform native oxide. This oxide was much different in character than what was observed previously. And so this is maybe a different picture. And so in the case of degradation, it looks a lot like rust, right? And in the case of the high quality oxide, it looks a lot like a SiO2 film, for example, that you would develop with, that you might deposit with PCBD or you grow in the oxidation furnace. And what really had happened in this case is what was happening is at room temperature, the aluminum was degrading by formation of aluminum trihydroxides. And that effectively led to etching of the material and decomposition of the material. And by raising the temperature, we're actually able to cross into the phase diagram to form both aluminum oxide hydroxides and aluminum Al2O3, which are much more stable forms of the oxide. And so again, you see some of the chemistry where, again, this is for the formation of the semiconductor to oxide hydroxide, as well as to Al2O3. And again, because you have a mixed aluminum gallium alloy, you can form a mixed aluminum gallium oxide system as well. And in Illinois, we studied a lot of properties of this oxide when it was first discovered. So included in this was looking at various kinetics. And so saw that high composition aluminum oxidized much faster than lower composition aluminum alloys. And Algas oxidized a lot faster than indium aluminum phosphide. And a lot of this you can pin back to the oxidation potential of the individual 3,5 column 3 elements. We also looked at a variety of other properties of the oxide, including the fact that semiconductors of different doping types oxidize at different rates. So specifically, P-type doping samples oxidize much faster than N-type doping, as well as had a higher temperature sensitivity as well. What we did characterize is that the oxides were robust, and we really didn't see additional oxygen or hydrogen from the process migrate into the semiconductor film in itself. And this was true for both Algas and the indium aluminum phosphide oxide. Other properties that we found from the oxide is that it was an excellent insulator, so breakdown better than 10⁶ volts per centimeter. It was an excellent diffusion max, so you can see here oxide over a superlattice, and then where you diffused in, it intermixed the superlattice. So the oxide was able to mask the diffusion and mask intermixing from the diffusion in the superlattice, and then it was low index, nominally 1.5 to 1.6. So with that new materials technology, we looked at what could we do to make better devices. And one of the first things that we did was look at making improved lasers where we were disordering. So we would diffuse silicon into the laser and intermix the material and form a high gap PN junction, as well as a optical lateral waveguide from the intermixing. But the problem is conventional devices had to have multiple alignments to align the diffusion and then to align isolation junctions on top of it. And what we found was because the native oxide was selective to the aluminum, that we were able to make a self-aligned process. So with that, we were able to, with a single diffusion step and a subsequent oxidation step, make high performance buried heterostructure single mode laser diodes that were just as good as ones that required roughly twice the processing. In addition, the oxide being very dense was able to serve as a hermetic seal. So one of the things that we did was we took red emitting communications LEDs within L-gas window and oxidize them post fabrication. And with that, we're able to form a hermetic seal around the window. And in addition, not just around the window, but around any types of imperfections. So these are cracks that originated at the side of the device from sawing, for example, in this case. And these were also sealed by the oxide. And what that enabled was the devices to withstand wet hot testing. So 85 degrees C, 85% relative humidity was a killer for these devices. It was a real problem. With the post-oxidation treatment, they were able to survive the 85 test on pass reliability. So these are the LEDs that people use for plastic fiber, optical fiber communications. The other thing that we came up with relative to using this new oxide was, could we use it to make index guided laser diodes? So by making the oxide, patterning it next to a laser stripe and making it go closer and closer to the active region, we're able to take a significant index step for the lateral mode that would be guided by the laser. And so with that, we made very index guided lasers using thick oxides in the L-gas system, as well as red emitting lasers in the aluminum gallium indium phosphide system. Later, it was determined that instead of going from the top oxidizing, that you could also go from the edge of the device and oxidize laterally. And this lateral oxidation could similarly be used for index guiding and current confinement to make a high performance index guided laser. And ultimately, then Dennis Deppy and his group at UT Austin did this for a vertical cavity surface emitting laser. And so with the oxide technology came the ability to make the lowest threshold and highest efficiency vertical cavity surface emitting lasers. And that has now become the dominant technology used in all the vertical cavity lasers out there. Well over 90% of all the lasers made use the native oxide for both index guiding and current confinement. So the first commercial applications of these were for communications devices, and this is work that we actually did when I was at Agilent Technologies, where we developed the first commercial 2+ gigabit per second VCSELs. And again, these utilize the native oxide on the edge. So again, we're oxidizing in from holes etched in the surface and creating an aperture in the device itself. And we ultimately scale these to arrays of 12 devices, and these were used prolifically for data center interconnects, and they still are today, albeit at higher data rates. But the biggest killer application was in your iPhone. So I don't know if people are aware of this, but your iPhone has a VCSEL array. It actually has one in front and one in back. This is used for Face ID, and this uses oxide VCSELs. So there are literally billions of dollars of VCSELs that are sold a year. And if you have an iPhone or an Android phone that's using Face ID, this undoubtedly uses arrays of oxide-based VCSELs. Okay, moving on. Now I'm going to talk some about compound semiconductor wafer bonding and how innovations in wafer bonding led to the realization of transparent substrate red, orange, yellow LED. So there are many different types of wafer bonding, and I've listed, I think, some of the main categories here. So people use van der Waals forces to bond wafers together. They'll use a metal eutectic to bond wafers together. Epoxies or even oxides in between two semiconductor wafers. What we're going to talk about today is the direct bonding of semiconductor wafers. So no inner layers, semiconductor to semiconductor to fuse two crystals together. And what's unique about this is that you can get excellent bond strength. You can thermal cycle the devices nominally up to the bonding temperature, so they're very robust to processing after the devices are bonded. We'll talk about, if you do it right, that you can actually get very low conductivity across the wafer bonded interface, as well as very good transparency. And in total, these properties allow you to make the best red, orange, yellow LEDs, and it's actually important in other areas as well. We'll talk about. That being said, and when we started on this work in the early 1990s, silicon to silicon wafer bonding was just being developed, but the bonding of compound semiconductors or 3-5s there was maybe one paper that was published at the time on this. Some of the differences are that you have a thermal expansion mismatch when you're bonding two dissimilar 3-5 materials together. The surface flatness is nowhere near the atomic smoothness that you can get on a silicon wafer. The surface volatility is high, meaning you have to worry about decomposition, especially of the column 5s. And that the electrical reactivity of the surface is also different. So based upon these, you just can't take the same techniques that people have developed for silicon to silicon wafer bonding and apply them to 3-5. So the first work that was done on this was done by Lau and Mull out of Lincoln Labs. And what they came up with was an apparatus where you have two pieces of graphite and you put the two wafers in between it, and you put that in a quartz cylinder. And then because of the differential in the thermal expansion coefficients of graphite and quartz, you could apply uniaxial force to the wafers. The problem with this is it was very hard to control when you actually applied and how much force you applied and at what temperature you applied it to. But nevertheless, they were able to fuse indium phosphide and gallium arsenide together, and they reported that in 1990. So we looked at that output and said, gee, if we could develop this technology further, this could be something that could be really useful to what we were trying to do with visible LEDs. So we developed a tool and a capability that was able to independently apply force and temperature. So two graphite anvils, and in this case, they're in a modified LPE furnace where we apply pneumatic pressure and can independently apply force and temperature. Also, very importantly, we developed a way of holding the wafers so they could be held
separate from each other and not have to be in contact before they were bonded. And so we could vary when the wafers went into contact. And then, I talked about not having wafers that were flat. Well, this gives you some example of what non-flat could be. This is a gallium phosphide wafer that is prior to bonding an LED set of layers where we removed the gallium arsenide substrate from it. So you're not just talking about variations in angstrom level RMS, you're talking about potentially have to deal with significant bow as well in the wafers. So with that tool, we were able to develop capabilities, and this really shortchanges all the work that we did to develop the bonding, but we're able to scale this and develop the ability to bond 3-inch wafers over large areas. And so this is a transmission picture. Similarly, we looked very hard at what was happening at the materials. This is a scanning acoustic microscope image. The interfaces were nominally void-free. And we were able to develop the capability such that from an absorption standpoint, this is the absorption edge of the as-grown epi. And then similarly, post-bonding, you see that there's really no difference in the absorption in the bonded materials. This is a transmission electron micrograph of an LED structure. And what you see, this structure is initially grown on gallium arsenide. We remove the gallium arsenide and then wafer bond the gallium phosphide. On top of it, it has a gallium phosphide window. That's why we can handle the wafer. And that window is about 45 microns thick. So there's lots of incline dislocations in the epitaxial gallium phosphide. But at the wafer bonded interface, they're nominally all edge dislocation. The one exception is, and this is purposely put in here, is if you did it under conditions that were too hot, you would see decomposition at the interface, and we would actually via mass transport get crystalline regrowth, albeit it was oriented in a different direction. So you have to stay under the temperature for decomposition to avoid getting these type of defects in the crystal structure. And one of the things that we realized in developing this technology that to get good electrical conduction across the interface when we fuse the wafers together, it was very important to effectively, even though the materials were lattice mismatched, was to align the surface orientation and the rotational alignment of the crystal. That wasn't something that was obvious to us when we were doing the work. So this is a schematic of 2 different wafers being bonded together with 2 different surface orientations and 2 different rotational alignment. And what we found was that, and this was true of every material that we tried to bond. In this case, we looked at N-type indium gallium phosphide to gallium phosphide. And as we changed the relative misalignment and rotationally, we basically could introduce a hetero barrier at that interface. And so we went from nice linear ohmic conduction to one that looked like there was a barrier at the interface. Similarly, when we looked at different surface misorientations, if we matched the surface misorientation or if we varied them by 6 degrees, we would see very different current conduction. So it's really important that align the crystal, even if it's lattice mismatch, across that interface. And we found that true to be true of N-type. We also found it true to be the same of P-type. We found it true to be true of indium phosphide, gallium arsenide. So this was one of the early learnings relative to what was important for wafer bonding. What we think is happening here is that, by having the different surface misorientations, you create additional defects or interface states. And those interface states basically pin the Fermi level and give you an additional barrier at the interface. And we would see this also in LEDs. So an LED that was fabricated with no misorientation could operate at good low voltages, whereas for a misoriented device, we'd see a significant additional voltage drop. when in a well fabricated device, we would also see no difference in the IV characteristics or where the N=1 to N=2 transition occurred between a non-bonded device and a bonded device. So we're not introducing any additional defects in the device by virtue of the wafer bonding. So we use this technology then to make high performance LEDs. And so we started with a aluminum gallium indium phosphide layer that was lattice matched to gallium arsenide, grew a metamorphic gallium phosphide window by VPE, etched the gallium arsenide substrate off, wafer bonded the two materials together. And then again, you see this is literally a 3-inch wafer of an LED and a gallium phosphide substrate. And with that, we produce transparent substrate devices. The wafer bond was very mechanically robust, so passed all reliability tests. So this is 17,000 hours of accelerated aging, projects out to over 100,000 hours of operation, as well as liquid-liquid thermal shock temp cycle and wet-hot humidity testing as well. So very mechanically robust interface. The devices went through a series of improvements. So we started with small chips, nominally 350 microns on the side, and then scaled them to larger power devices and shape devices over time. So these were the first devices that exceeded 100 lumens per watt, LEDs that exceeded 100 lumens per watt. They still are the most efficient red LEDs. So at this time, this was 55% quantum efficiency in the red. And these were used and have been used in a variety of applications, from traffic signals, road lighting, turn-tail stoplights of cars, moving message panels. And that's all underpinned by this compound semiconductor wafer bonding technology. I'm going to shift gears another time now and talk about work that we did at Infinera on indium phosphide and silicon oxynitride materials engineering, and ultimately what that led to in terms of being able to develop photonic ICs for communications. This case, I'm going to not be able to go into as much details on the indium phosphide because a lot of this is still held as trade secrets, but I'll give you some of the flavor for some of the things that we've developed on the material side. I'll talk more about some of the work that was done in developing deuterated silicon oxynitride for very low loss waveguides in passive photonic ICs. So things that we did that were, we started Infinera in 2001, and things that we did that were beyond what is known in the literature are some new techniques around growth and regrowth, as well as selective area growth. Also, there are things that people don't appreciate about some of the band structure, believe it or not, even on a mature technology of indium aluminum gallium arsenide. And probably most importantly, a lot about defect and impurity engineering. And with this, we were able to, and I'll show you, have record laser performance, the narrowest line width indium phosphide based lasers, the highest performance modulators. And with this, we're able to scale the integration to be able to make some of the most sophisticated photonic ICs that have been developed for communications. So I'm not going to spend a lot of time because this is more device centric and the intent is to be materials centric in the talk, but this is the first devices that we made at Infinera using those capabilities were 100 gigabit transmitters and receivers. So here we're integrating over 50 devices on one chip and over 10 devices on another. These were the first 100 gigabit per second devices that were deployed. We scaled that ultimately to integrate 1,700 devices. This was in the research laboratory. The previous one was commercialized. And you can see the chip here, and this has 40 lasers on a single chip and 40 nested Mach Zehnder modulators here. And you can see the performance is all overlaid on top of each other. Oh, coherent technology. So this uses quad-chip phase shift keying. And again, you see devices here. There was a lot that went into the development to make this. This is a very circuitous layout for the PIC, and this uses coherent technology that on the transmitter is heterodyne with a local oscillator that's integrated, monolithically integrated in a receiver chip. We ultimately also developed tunable lasers on this technology. And again, this will be a little bit relevant relative to where we're headed in gallium nitride. And with those tunable lasers, we can tune over 50 nanometers in the infrared. In this case, we integrated 6 lasers on a photonic IC. In the research, and this was a commercial product. In the research lab, we integrated 14 widely tunable lasers, and that gave a capacity of almost 5 terabits per second on a single chip. And so it talked a little bit about some of the materials innovations, and one of the things they really enabled was the ability to make the lowest, highest performing modulators, which is a combination of loss in the modulator and how much voltage it takes to modulate the modulator. And so the devices at Infinera are actually off the chart relative to conventional 3.5s that have been made relative to have low loss and low voltage modulation. And a lot of that goes back to the materials developments that I talked about earlier. In addition, the lasers on these devices were 40 kilohertz in line width. So at the time, these were the narrowest line width lasers that were reported. And the devices were highly reliable. So this is 40,000 hours for a chip that's got over 50 functions, has the same reliability as a single submarine pump laser. Now I'll talk a little bit more about be able to go into a little bit more depth about a platform, and we're in the process of bringing this platform up in the internet, by the way, called HIDEX. And what HIDEX is a platform that uses deuterated silicon oxynitride. And what that does is, by using deuterated sources instead of conventional silane and ammonia, we can push the vibrational mode in the absorption for the silicon, oxygen, hydrogen that's normally at 2.73 microns all the way out to 3.74 microns when it's deuterated. And because we push that out, we then lower the absorption in the infrared, and we actually lower the absorption, I'll show you later, in the visible as well. And so in this case, this is work that was done that shows a 30x reduction. It's actually over 100x when you work to really get all the kinks out and make it in devices. So you go from dB per centimeter losses to dB per meter losses in your waveguides. So with this deuterated, and what's also important is there's other ways you can get the hydrogen out of your film. One way that people commonly do it in silicon nitride is they just heat the film up. And they'll heat the film up to 950 degrees C and anneal it for 8 hours to get all the hydrogen out. The problem is compound semiconductors, 3.5s, don't like to be annealed at 950 degrees C for 8 to 10 hours. So this process is not, silicon nitride with that kind of low hydrogen content hasn't been readily integratable into the devices. What's nice about using the deuterated sources is you can use them with PECVD. So that drops the deposition temperature down to 250 to 400 degrees C. And now I have a process that is low hydrogen content that I can put into the process of my device. I still got to worry about my hydrogen budget. So I got to worry about what other processes that I put in so it doesn't add hydrogen back into the film. But I can make very low hydrogen content films and use those for waveguides in my device and integrate them right into the chip. So in fact, this is what we did at Infinera. We purchased a company that had this technology called Little Optics. This was back in 2006, and then we further developed the technology at Infinera. And you can see some of these micro ring resonators. These have heaters integrated upon them, and with this, we can make very sharp gigahertz bandwidth tunable filters. And so this is actually a commercialized device that we deployed at Infinera. That was an optical add drop multiplexer using this low loss glass. And because we could use the low loss glass, it was many dBs less loss than you would have if you would make it an equivalent. But you can also use this to make very long spirals, right? Because we're talking about dB per meter losses, not dB per centimeter. And so there's many things you can do with that. One thing that people are doing today are making very low loss extended cavity narrow line with laser. Another thing you can do is make programmable delay lines. So you can see that, in this case, we're able to get over 250 picoseconds of delay optically because you can make very long spirals and meters of waveguide kind of similar. So now I'm going to pivot and talk about trajectories that we have here at NC State, and we're about 3 years into setting up the capability, and I want to acknowledge all the great work for the team that's in our group, as well as Jonathan Weir, Spiros and his group, and Zako and Sedchi. So I'm going to talk about some of the work that we've been trying to kick off on trajectories to engineering wide bandgap and ultra wide bandgap materials. And we're hoping that will take us. So why do we care? At least three reasons why we care. One is that there's been innovations about taking gallium nitride based LEDs that can operate at 10 gigabits per second and 150 degrees C. Well, what does that buy you? Well, today, if you look, a microprocessor is rapidly approaching, especially the high-end devices, where we consume as much power for I/O as we do in compute. And when that happens, we roll over when we have to, in terms of how do we scale. So we have to solve the I/O problem. So people are working real hard electronically. How do you solve the I/O problem? But we're really running out of gas in terms of what we can do in terms of driving interchip I/O. So people are looking optically. One of the problems optically is that all of the schemes so far have used lasers that interconnect the chips. Lasers do not like to be at 105 to 125 degrees C junction temperature. So as a result, we have to put the laser remote to where the processor is. And when we put the laser remote to where the processor is, now we have to worry about the link between that laser and the processor chip. So inherently, we have extra electronics, we have extra drivers, all those kind of things. What you'd really like to be able to do is have a device that you can put right on the processor, that you could interconnect right to the output transistor of the signal on that processor and drive an optical signal. But if the devices can't withstand that kind of temperature, you're out of luck. So we've been this startup company out in California demonstrated that they could get 10 gigabits per second out of an LED at 150 degrees C. And then this is a technology that people are scaling micro LEDs for displays. So they scaled this in an array form to make work towards making terabit or multi-terabit level interconnects for chips. And if you can do that, and you can do that without any of the additional electronics, any of the SerDes, those types of things that are required, you now can change how you architect the processor. And so you can talk about disaggregated processors. You can really change a lot about what the future of interconnectivity looks like down to the chip level. So this is one reason that we care about scaling and what we could do for gallium nitride optoelectronics. Another reason we care is that if you look, most of the molecules that exist, period, have vibrational signatures in the ultraviolet invisible. And with spectroscopy, we can see those signatures, and we can then detect what's there and then use those signatures to, in a variety of ways, for environmental health medicine. But today, all of these systems exist in a laboratory bent scale in general, maybe if we're lucky, a toolbox in some instances. And then third reason is quantum photonics. So there's a variety of approaches to quantum photonics. Some used liquid helium cooled electronics and superconducting physics. But one of the approaches that people are looking at really use ion trap cooling. And ion trap cooling has the vast majority of the photonics that are required are in the near ultraviolet and visible. So there's lots of applications to, and today, if you look again, these things sit on massive optical tables with very high performance racks of gas lasers or fiber lasers today. And so there's a huge opportunity if you want to scale to get from 30 to 50 qubits to 10,000 qubits, you have to do something fundamentally different, which is put a lot of that optics on a chip or multiple chips. So these are three big reasons why we care. There are others too, but these in and of themselves can be very transformative. So that being said, there's barriers. Why can't we just take, there's been all this technology that we just talked about and showed in the infrared. Why not just apply it to gallium nitride and we can start attacking all these? Well, there's some very key gaps. So today we don't have low loss waveguides in the visible and ultraviolet. There's just been some recent reports, but they're, if anything, just starting to be born. We don't have tunable microresonators. We don't have the ability to put an active device like a laser or an amplifier next to a passive device on a single chip, or have an integrated laser. So there's blue-green lasers, but they're all single chip lasers where the facets are nominally formed by cleaving. And then we don't have tunable lasers, nevertheless, spectroscopic grade tunable lasers where we have very narrow line length. And then the full toolkit of modulators, detectors, etc. So why don't we have these? Well, the wide band gap materials have a significantly smaller index step, and it really makes mode confinement challenging. So it limits what kinds of devices we can make. We also can't translate a lot of the processes from indium phosphide. Regrowth and selective area growth don't operate in the same way in the nitride materials as they do in indium phosphide. Nitride process technology is inherently high temperature and limited, and because it's high temperature, it's generally limited to the surface. So trying to do deep processing, like I showed earlier on, where we're diffusing silicon, a micron into a device and making a buried heterostructural laser, is that something you can readily do in the nitrides. There's also easy to do defects in the processing. And there's also a high CTE mismatch of the alloys and the substrate. So all these makes things much more challenging than nitrides, and why we can't just plug and play what we know in the arsenide phosphide. So what we've been trying to do is develop a suite of capabilities to start to attack how do we solve some and make new materials innovations that then can build these. So one of them, and I'll talk more about this, is what we call a crystal heterogeneous integration reactor. So what this does is it takes the wafer bonding technology that we developed at Hewlett Packard, and it fuses it with the gas handling system of a MOCVD tool. And that gives us a unique capability, and I'll talk about that and as well as what that can do. Some early results that we have for that. We do have an MOCVD reactor that will help us to develop some of the crystal structures, and we can do this both at atmospheric and low pressure. And the plan is that we're going to use this to try to develop some of the innovations so that we can do regrowth and selective area growth in the nitrides, albeit with different constraints to develop some of the photonic integrated circuit devices. One of the things that John Weir developed at Lehigh was the demonstration that you can oxidize indium aluminum nitride films. And this is actually significant because prior to this, the ability to oxidize aluminum gallium nitride, because of the high stress, limited you to very thin oxides. So in this case, you can get 1,000, maybe even more angstroms of oxide without having stress and delamination and defects propagate. So that again opens up new avenues that we can use to make better optical devices. We have a capability in the NNF that we have not yet turned on. We still have to invest in doing this, but with it, we have a sputter tool that we will be able to do reactive sputtering. And with this have indium aluminum gallium nitride oxide dielectrics. And again, the idea there is we have a wafer fab technology that can have sputtered oxides, basically. And then we're also in process of standing up these Hydex films. So Infinera has been kind enough to allow us to take some of the recipes that we had for that, and we're going to stand that up in the NNF. And what's very interesting about this is there's just been some recent reports. So this is a work that extended the infrared. So there's not been a lot of study or reports of silicon nitride in the visible, but this is not Hydex, but this is silicon nitride that shows basically a dB per centimeter in the blue. But again, this is a silicon nitride that people have annealed at 900 degrees C plus for many hours, right? So our hope is that we're going to be able to take this Hydex film and be able to now have low loss dielectric waveguides in the visible that we can integrate into our device. With that, we're good. And I'll talk more, but the wafer bonding capability that we have will allow us to have buried device structures, and it'll allow us to mix and match alloys that we can't readily put together with to grow epitaxially. We have to grow them on two separate wafers. With that, we can make buried ridges. And we also think we can overcome some of the limitations that exist today in doing selective area growth by basically embedding certain patterns in the wafers before we grow on them. So this is a little bit more about the we call it a CHI reactor. And so this is a picture of it. It sits in the bottom of MRC. And again, it uses that same technology, but we've also added the capabilities to have a column 5 overpressure, column 3s. We can do in situ etching and in situ doping. So if you think about it, we're literally applying 1,000 pounds of force at 1,000 degrees C in the presence of toxics, right? So it's taken a lot of engineering to develop a tool that could do that. But with that, we believe we've got some unique capability to build engineered substrates. I'll talk a little bit more about that. To do decomposition-free bonding. And so I talked a little bit before and showed some of the limitations that if we get the crystal too hot, we see some of the defects that are formed by having a column 5 overpressure in the tool. We greatly enhance the process window that we can explore to integrate materials. We can also, because we can etch or dope, also engineer the interfaces before we integrate the devices. So a little bit of what is different. So we're able to keep the wafer separated. We can vary the force with time and temperature. And today we've got ammonia, TBP for phosphorus, and TBA for arsenic. And we're going to put. We also have silane in the tool, and we're going to be putting CP2 magnesium in as well for P-type doping as well. We can go up to 1,000 degrees C, and we can apply much more force. So one of the things, might ask, well, you've got that bowed wafer, how do you deal with that? So what we do is we heat the wafers up to a point where we get past the ductile brittle transition. And when we do that, then we apply force. And in doing so, we can basically flatten out the wafers. That works for gallium nitride. So it turns out we found that around 800 degrees C or so that we can get past the ductile brittle transition for gallium nitride. It obviously doesn't work for aluminum nitride. That's much higher temperature. So there's still more to be explored there of what it means for some of the alloys as well. There's some of the results that we've been able to achieve. So we're able to bond freestanding GaN to GaN. So all the samples we do are nominally a centimeter because we're trying to be sensitive to cost, but we can do larger areas. So this is the bonded interface. And again, one of the things, and we see this very readily, when we use ammonia as a environment where we're doing this, we go from a situation where we see periodic voids at the interface and generally weaker interfaces. In the presence of ammonia, we were able to eliminate the voids and have much stronger interfaces there. And one of the key things that we found when we were doing the LED work is actually one of the most stringent things you can do to test the strength of a wafer bond is to saw two wafers. And that's even more stress than thermal shock or all kinds of packaging. And so we're able to readily saw all of these things here on the gallium to gallium nitride bond. We're also able to bond gallium nitride and silicon to freestanding GaN, even despite the thermal expansion mismatch in silicon. Do that, and again, you can see the bonded interface here. GaN on silicon, GaN on silicon, and most challenging GaN on silicon and GaN on sapphire. And so what does this enable us to do? So in many cases, we like to embed certain things around an active region of a device or two-dimensionally. And so it's real difficult to do that if we're processing everything from the surface in gallium nitride. So what we can do is we can think about taking a device structure and effectively stop whatever point where we want that processing to do, and then build another wafer with the other half, process the wafers, and then put them together. So we can make embedded structures, and that really can benefit LEDs, lasers, HBTs. And so this is an example of some of what we're able to do. So this is a pattern structure, and you can see a closer up view and even a cross section. And these are things, the first work that we're doing here will be towards making passive waveguides with those embedded structures. And one of the things we've been doing is, as we've been learning about what materials we're able to put together and put in combination, building and designing what would be our platform for the visible and ultraviolet PICs. So this shows an active, so not only a laser gain region that's going into a passive waveguide in a stacked structure. And again, we're going to build this by breaking the device in half, processing it, and putting it together. And you can see that we can have a mode transition that goes from the active to the passive. And I didn't show all the modeling results here, but we can make this transition with less than 1/10 of a dB insertion loss, and most importantly, with less than 60 dB of back reflection. And this actually winds up being really important. The people that are trying to make a lot of these PICs for quantum photonic applications, the devices are really limited by back reflections in the device. And today they use a lot of silicon photonics trying to do this, or SiO2 in combination with external cavity devices, and the back reflections there just kill you. But what we're able to do, because we're making this monolithically, is get very low back reflections, and that should be able to allow us to have really interesting performance. In fact, we were just at a quantum electronics workshop, and they basically said, gee, if you could do 50 dB back reflection, that opens up a whole set of applications for what we could do. And so we think that platform is consistent with that. We talked about, I won't talk further about the LEDs, but in the mode of trying to develop and engineer better LEDs, Alex Chow in our group has brought with a capability for modeling called the effective bond orbital model. and Alex can speak much better to this than I can, but basically the idea is instead of using the individual atoms as the basis for the calculation as you do in VFT, you use the unit cell as the basis. And that winds up being a much more computationally efficient way to calculate band structure. And when you do that, you then taking all of your computation time to calculate what happens in the bulk to being able to implement for more complex device structures and heterostructures. So this is example of work that Alex did for his PhD at Illinois, but basically he was able to, with this effective bond orbital model, match the DFT calculations, albeit in more than an order of magnitude more efficient calculation. And so what the work that we've done here is looking at what type of LED structures people are using for some of these high-speed LEDs, and developing a full band structure based upon this modeling capability. And with that, we've got designs that would seem to indicate that we can more than double the types of bandwidth based upon what people have done, based upon the band structure and the calculation of the ABC coefficients that would come from that band structure. So this takes into account just not radiated recombination, but Auger, which is really important. And it's not been something that people have been readily able to model. So this is actually, we think, going to be a significant capability to be able to model the band structure of these kind of sophisticated devices. And should lead us to hopefully better LED design. Additional things that we're working on is pushing the heterogeneous integration envelope further. So there's different places you can put the interface. So you can wafer bond where the interface is remote to the device, and that's what people do in 2.5 and 3D packaging. You can make it remote to the active region, and that's really what we did in transparent substrate LEDs. It's what people do in heterogeneous integrated silicon photonics. But what you'd really like to do is make that interface integral to the active region, meaning within the depletion region. And if you do that, you really could make very different kinds of HBT, FET, and laser structures. The problem has been it's not been viable to date because of the high defect level. So work that we've been doing in conjunction with Spiros's group and Zlato's group has been, could we make a nitrogen arsenide PN junction with low enough defects that would be would make a better HBT? And if the calculations that Spiro has done here said that if you could do that, you can make an HBT that's substantially better than the state of the art what people use today for InGaAs indium phosphide, right? More than 10x better. So with that, we've between our groups have been working to integrate these InGaAs to gallium nitride junctions. This is a picture. This is just the edge of a wafer of a 1 centimeter by 1 centimeter device. Here's an SEM cross section with GaN bonded to InGaAs. And with this, we've obtained defect levels that we think are substantially lower than what people have attained by doing similar work to this, and better PN junction results. So I think there's still a lot of work to be done to actually get to the point where we can make a good PN junction interface to make a good HBT. But I think we have the best capability to do that here. The other thing that we're working on is engineered substrates. So there's been a lot of what I would say is bad science around engineering substrates, where people have suggested that you could actually use elastic relaxation to generate low dislocation material. But there has actually been some, I think, some real interesting work where people have actually used plastic relaxation. And they've done this both in silicon germanium and in InGaN and Splaytech. But one of the problems here is that this work has generally been limited to small islands on material, and because of buckling, because of the surface tension of the material. So when I go to relax it plastically, the material buckles. So we believe with the capability that of the tool that we talked about, the CHI tool, that we can overcome this and do this in large areas. And if we can, it opens up, we think, all new kinds of opportunities to basically make ternary substrates for and opened up the ability to use new alloys. So this just gives you some idea of just from the laser perspective where some of the limitations are, but there's real gaps in terms of laser efficiency, not just in the visible, but in the infrared. And so one of the things that we have looked at is if we can make and be on a ternary substrate at 1.3 microns, we can actually, again, drastically change the efficiency and the temperature even of 1.3 micron lasers. And again, if you could do this, you can similarly put lasers on the processor. And so what we've developed is a capability where we can put 100 angstrom films. This is strained on BPSG, so we still have to relax it, but we're actually able to see this 100 angstrom film with PL. And what's pretty unique about this is it really gives us a tool to probe. The people that were doing this plastic relaxation in InGaN because it's so defected, because they use smart cut to remove it, had to go to a synchrotron to be able to see it. And doing experiments through a synchrotron where you're trying to do process development in semiconductors doesn't really work. So, those are some of the trajectories that we hope to engage to really develop the next generation of capability for visible and ultraviolet photonics. And then one of my favorite sayings.
Any questions?
Yeah, thank you, Fred. So you threw a lot of technology at us and
It's more
also
moving,
give
yeah.
give an interesting historical perspective. So which I hope that the students appreciate a little bit. But just maybe one simple question. You showed the LED development and the facet for the extraction.
Right.
So how was the pyramidal faceting done on those? Is it just etching?
Sawing and then etching.
Sawing and etching?
So you use an angled blade, and that angled blade would, so you turn the wafer upside down, use an angled blade, and that would create the pyramid, and then you would go back with a post-thaw etch and clean up the damage.
Okay, so the etch is just cleanup. It's
Yeah,
not actually,
I also have a question. You mentioned that you for using near infrared photonic IC, the waveguide loss is low waveguide loss is not available, right? You not able to, so you have to, that's why you need to go to UV. Is that what?
No, so in the infrared now, you can get dB per meter type of losses.
Right. Okay.
In the semiconductor, you're typically dB per centimeter,
Right.
right? One of the real problems in the visible and the ultraviolet is people are generally 5 to 10 dB per centimeter.
Okay.
Right, and that's why the result that I showed in silicon nitride, where it was below a dB per centimeter, is remarkable in that way, and that starts to open up something that could really look viable. Because if you're losing 10 dB per centimeter on your chip, you're never going to make a photonic integrated circuit, right? So it's really, you got to get down to the dB per centimeter or lower if you're going to have a viable photonic integrated circuit technology.
So you have to appreciate the problem, because the scattering goes as lambda over the fourth power,
Yeah,
1 over lambda to the fourth power. So same feature size when you go to 3 times lower lambda, it's now suddenly whatever 64 times.
Right, right. So what those devices at a dB per centimeter are limited by scattering loss. They're no longer limited by absorption loss from the hydrogen, right?
So the reason you need to go to shorter wavelength is because of the temperature stability of the nitride system, right? Compared to arsenide or.
Well, we want to go to shorter wavelength to be able to attack those applications that we just talked about, right? So we need the wide band gap for the visible and the ultraviolet. wavelengths, right? We need the wide band gap for the high temperature LEDs. Right?
Okay. Any question? Okay, let's thank our speaker one more time. So what's the?
Was that
Yeah.
too high a level or? I mean, I could have gone
No,
into a lot more
No,
depth.
no, I think it's fine to give people overview. What is there. Well, thank you very much.
Sure, thank you, Frankie.
Okay,